Okay, good afternoon all of you. My screen is visible?
Yes, sir.
You can see that some small derivation part of characteristic AC harmonics. As we discussed in the previous class, harmonics we divided into two categories. One is the characteristic harmonic, another one is the non-characteristic harmonic. So that we can see in the previous slides also. You can see that this is just a review of previous class. Characteristic harmonics always present even in the ideal condition cases also, like balanced AC voltage, symmetrical three-phase network, and the equidistant pulses case. So all in normal cases also there is a harmonics will be present because of the controller are there in the source side as well as the receiving end side. Because of the power electronics controller, there is a harmonics will be injected. So that harmonics may not be only AC harmonics. There is a DC harmonics also there. For that, based on the pulse number, it will divide the order of the harmonic in the case of AC side as well as the DC side. And also we noticed in the previous class, once pulse number increases, some of the lower order harmonic is going to be suppressed. That also we observed based on the pulse number, whether pulse number is 6 or pulse number is 12, automatically it is going to be changed their order. That shows that lower order harmonic is going to be suppressed by increasing the pulse number, and hence reduction of the higher order harmonic is simple than the lower order harmonic. So that also we noticed. Another one is a non-characteristic harmonic. In this non-characteristic harmonic of order other than those the characteristic harmonics. So characteristic harmonics H is equal to NP, then NP plus or minus 1. It is in the AC side and the DC side. And other than this order, I call it as a non-characteristic harmonics. So in this there are due to the imbalance in the operation of two bridges of a 12 pulse converter, firing angle errors. So these are the reasons. One is the imbalanced operation on the 12 pulse converter. There is a 2 6 pulses are there. If any imbalance takes place, then it will induce the non-characteristic harmonic. And unbalanced and disturbance in the AC side, and then unequal resistances or leakage reactance in the transformer feeding to the two bridges. Under these conditions, we'll get it as a non-characteristic harmonics. So converter, there is both AC and DC harmonics which are injected into the AC side as well as the DC line side. Now there is several problems associated in injection of the harmonic. As you are aware that once it any side, it may be load side or in normal case also, even in when you are operating as a machine or something, anything. So once harmonics are injected, there is a problem will be there. So the injection, whether it is in the AC side or a DC side, there is several problems will be there. Telephone interference. These are all already explained in the previous class, first two slides. Then we'll start small derivation. Extra power loss that leads to the heating, and over voltage due to the resonance. Instability of the converter controls, that is primarily with individual phase control, scheme of firing pulse generation, interference with the ripple control system used in the load management. So all these are the some of the problems, and AC filters are invariably used to filter out the AC harmonics which are critical. That's what I told you. In the DC filters are you can use directly as a what you call it as a smoothing reactor to filter out the DC harmonic, but little bit AC harmonics critical. And the AC harmonic, the filters are, band power, also called as a tuned filter or high pass type, supply the reactive power. And DC smoothing reactor along with the DC filters perform the function of the filtering DC harmonics. And in addition to the harmonics, there is a telephone interference at the carrier and ratio frequencies are also generated by the converters by requiring suitable filter. The harmonic generation and various types of filters used in a converter we'll discuss in this. That's what I mentioned. No, once if I increase the pulse number, automatically order of the harmonic, you can see that for the DC side 6, 12, 18, 24. But whereas in the 12 pulse converter, it starts 12 and 24. What about the 6 and 18 is automatically suppressed. Same thing in the AC side also. We can notice 1, 5, 7, 11. But once if you go to 12 pulse converter, 1 and 11 and 13. So only 11 and 13 fundamental harmonic will be there, but 11 and 13 you can use to suppress the harmonics. And again 17, 19 not be there, and 23, 25 will be like that. So you can able to minimize the lower order harmonic if I increase the pulse number. That's what so far we noticed. These all we discussed in the previous class. And now we'll see one of yes, just a minute. And these are all characteristics harmonic positive sequence. So this already covered. And now this characteristic harmonic, this is the controller. There is a 2 6 pulse converter connected in series, and we'll see that what is the total current IA passed through the controller. And one thing is some information. I will give assignment in the LMS server today. You just complete that by within 2 days. So that we'll start anyhow you may be there in the second mid also as well. And before that I need to conduct a second slip test, second assignment. That's why I will give today 2 questions. You just write that 2 questions and submit in the LMS itself by maybe today is Monday, no, Tuesday, Wednesday. So you just submit on or before Wednesday, only 2 questions. I will give it to you as an assignment. And then we'll see that second slip test I will announce you shortly, and the syllabus for the second slip test and all, and also second assignment. So these are the internal part is left out. You just complete as soon as possible so that you will be free for main exams and all. So second mid and all. And now we'll see there is a current in the first transformer, means first controller, star connection, and then delta star or star delta. Let it be. We'll see that as a delta star we can connect. And now there is a 2 transformers here in the side, and there is a controller 1 and controller 2. This one we call it as a smoothing reactor. So AC current waveform you can see, it is not a DC. AC current waveform in IA1 and IA2. Then some current is IA1 plus IA2, that I call it as a IA. And consider 12 pulse converter what we shown you in the using as a Fourier series by applying that waveform. And in this case we neglect the overlap period. So I will show that if overlap also there, what is the modification in our equation, the current expression. But let's consider initially there is no overlap, and what is the current. And also we can see that transformer ratio primary to the secondary 1:1. That shows that in the supply side and wall side voltages are same. And then this is the just previous diagram only, IA1 and IA2. And in the 12 pulse converter, if you apply that Fourier series analysis equation, IA1 is equal to 2 root 3 by pi ID into that harmonic expressions, the fundamental 5th order, 7th order, and so on, 11th and 13th. So this is the IA1 expression. And similarly for IA2, and same 2 into root 3 by pi ID into expression for IA2, and you simply add these 2 expressions. Delta star connection of a transformer, turns ratio is root 3 into 1, because delta star connection you can consider. and then IA is equal to IA1 plus IA2. Some of the harmonic is going to be suppressed by adding this, because it is obviously as a 12 pulse converter. Previous expressions are only the 6 pulse converter, and if we consider as a 12 pulse converter, automatically some harmonics is lower order harmonic is going to be suppressed. As we noticed in the table also, in the 12 pulse converter, we will start with 11th and 13th order harmonic, again 17 and 15, 17 is missing, and again 23 and 25 harmonic. That is also observed in the table. And from the above expression, we can see that I10 or not. So that indicator second term suffix is indicate that overlap period is 0. So means let's consider no overlap. In that case, we can see there is a 0 instant. Another one, we can 1 and H. So that indicate 1 indicate that fundamental and H indicate that as a harmonic order. So based on whatever order you want to consider, that we can see from that above expression, you can see the 2 into root 6 by pi. That means that 4 root 3 is there, no? So into ID, that 1 2 will keep inside. So if it go 2 in the root side, we will get it as a 4. So 4 into 2. I mean, you can see that this expression will get it as a in terms of the I01 fundamental expression. So that will write it in terms of the fundamental equation I01 and IH0, or we call it as RMS values of the fundamental. So RMS means again root 2 will be there, that root 2 into root 3 will get it as a root 6, the fundamental component, and order of H. The second suffix I already mentioned, no, it is, we call it as a overlap angle. Let's consider overlap angle is 0, then the current will in the fundamental, current in the order H order harmonic, you can represent like that. And if you consider as a non-overlap, that means that suffix is not be the 0, some maybe overlap is less than 60 degree or greater than 60 degree, like that. If I consider that, then IH will get it as this is generalized expression you can mention, but all in detail of how we are getting A, B, all these constant and all, it will become as a huge derivation part. So that won't require. It is only the order of the harmonic current. If it is a non overlap period, I mean overlap period is 0, then we will get it as a previous expression. Now overlap period is present, that means non-zero case. So we will get it as a ABC, and where delta is equal to alpha plus mu. Mu is nothing but a overlap period. That overlap period is less than or equal to 60 degrees case. Preferably the above expression is valid up to 60 degrees only. And suppose if your overlap period is above that expression, then you can simply modify your expression alpha dash, u dash and del dash, so that you can replace it. Alpha dash is nothing but alpha minus 30 degrees, u dash is equal to what you call it as u plus 60, and so on. These are the modifications are required if overlap period is greater than 60 degree. Preferably in the all the expression, overlap period is always less than 60 degree. As you noticed in the second unit also, based on the overlap, if overlap period is more than 60 degree, less than 60 degree or equal 60 degree, all these instant the conduction intervals is going to be takes place. Suppose if it is less than 60 degree, there is a 2 wall conduction and then 3 wall conduction, exactly equal to 60 degree, all instants 3 wall conduction is taking place, and greater than 60 degree 3 wall and 4 wall conduction is going to be happened. So all these depends upon the overlap. So it is only the instant once if the source is having more impedance, that we call it as incoming and outgoing devices are going to conduct in that aspect. That is the reason many number of devices, whether it is in the positive group or a negative group, the devices is going to conduct. And then you can see that effect of the overlap angle is to be prevent the step changes in the AC current. This implies IH is smaller than IH naught. For example, alpha is 15 degrees, overlap is 25 degrees. 11th and 13th harmonic currents are reduced to about 0.25 into IH naught. So this is just analysis from that. The magnitude of the characteristic harmonic also function of the load current. Now you can see by the load current is x-axis, and if you see the harmonic current IH by variation of different harmonic quantity, let it be H is 5 and 7, 11, 13 and so on, you will get this is the flat. But as you are aware that always lower order harmonic magnitude will be high when compared to the higher order harmonic. That is only the reason, this is one of the reason you can say that an HVDC converter will use as a 12 pulse converter. That is only the one reason. Other reasons also there, you can reduce the ripple content, all these things, and power improvement, and these are the main factors, because large power need to be transmitted. It has to carry the current carrying capability. Because of all these reasons, preferably we will consider as a 12 pulse converter rather than 6 pulse converter in a HVDC system. And now we can see that DC voltage harmonics. As you noticed in the previous slides, there is a AC voltage harmonics. Now we'll move on to DC voltage harmonic. From the Fourier analysis of a DC voltage waveform, we can get that VH is equal to VD naught. So this is the C square plus D square minus 2 CD cos of that expression. We'll get it as a relation of DC harmonic. And non-characteristics harmonic, as you mentioned in the previously, there is a characteristics and non-characteristics harmonics. In that notice, we have one relation. There is a other than the characteristics harmonics, we call it as a non-characteristics harmonics. That is, one is a characteristics and non-characteristics. Characteristics, we observed that H is equal to NP, and then DC side, and AC side is NP plus 1. Like that, we can observe that other than this order, we can consider as a non-characteristics harmonics. So that we can see that harmonics of order other than this characteristic harmonics are termed as a non-characteristics. And why this will happen? So that is there is a due to imbalance in the operation of two bridges. That is one thing, and firing angle error, and then unbalance and disturbance in the AC voltages. Just a minute. Now you can see these are the unbalance and distortion in the AC voltages, like just previous slides also mentioned same points for non-characteristics. Due to these are the reasons you will get it as a non-characteristic harmonics, mainly due to the difference in the firing angles. That is, we call it as a firing angle errors. So as you are aware, for the 6 pulse converter itself, once if you have just consider for 6 pulses converter, whatever may be the device conduction, let consider something maybe device conduction, something like that, and just for example I am writing. So if this instant device 6, 1, 2, 3 and so on, if it is conducting, then firing angle error, in the sense, instead of this instant, the firing pulse is missing and it is conducting after this instant. So then what will happen? At this point, it will not be conduct exactly at that point. So then it is going little bit later point of time. And similarly, some other device also, if it error is occurred, then instead of firing like this, it may fire like this. So that is the can say that firing angle errors. So in this two bridges which lead to the unequal calculations of the harmonics of order 5, 7, 17, 19, etc. And the unequal leakage impedances of the two converter transformers feeding the two bridges also lead to the residual harmonics. So unequal leakage impedance, as I mentioned previously, two transformers are there no in the converter 1 as well as the converter 2, and these two transformers are feeding two bridges obviously, because one 6 pulse converter, another one is another 6 pulse converter. This set of star star and then delta star transformers are connected to the two bridges. That is, first bridge is a 6 pulse, another bridge is another 6 pulse converter, and also lead to the residual harmonics. And the last three cases can lead to the generation of the triplet and even harmonics, and analysis is complicated. So triplet all the multiples of 3. So that harmonics analysis is a little bit complicated. So harmonic filters, we can see that what is the purpose of harmonic filter and all. So we can see that one thing, there is a AC harmonic filters serve two purposes. That is one is to reduce the harmonic voltage and currents in the AC power network to acceptable level, and to provide all or part of the reactive power consumption by the converter. So these harmonic filters, now we'll move on to the filters. So as you notice in the previous slides and all, harmonics. So what are the types of harmonics are there, the characteristics and non-characteristics. If harmonics are injected into the lines, what are the causes for that, the effect of that. And another one is why non-characteristic harmonics are injecting, and what are the AC values and the DC side. All these things we discussed in the previous. Now once if you are aware in the harmonics, now what is the other part is how to eliminate that harmonics. So for that we need to design as a filters. So the lot of filters are there in the what you call it as AC filters and DC filters, like that. In HVDC station, many number of filters need to be installed in the converter side as well as the inverter side, or you can say that the rectifier station and inverter station, and source side means the before wall and after walls, I mean the DC side. So lot of filtering are required, and while you are designing that filters, we need to select the appropriate harmonic. You have to tune that, and particular frequency of the harmonic is going to be reduced, so we have to eliminate. So like that we need to design. So this is the purpose of the harmonic filter. AC harmonic filters serve two purposes, because as I mentioned, no, there is a two types of harmonics. One is a AC harmonics are also there, and then DC side also there. So for AC harmonics, we'll do the, I mean, filters will do the two purposes. One is to reduce the harmonic voltages and currents in the AC power network to acceptable level. So while you are designing itself, we need to take care of that, what type of filter we need to design and what is the frequency of harmonic we are going to eliminate it. So that is the reason we can see that two purpose. One is to reduce the harmonic voltages and currents in the AC side up to the acceptable level, and second one is provide all or part of the reactive power consumed by the converter. So here this is also one of the major factor in the compensation. Normally reactive power compensation is required, but these filters will not supply total compensation, but some part of that is going to be compensated. Rest of that part who will supply, that is what they mentioned there itself. So this is the some part of the reactive power consumed by the converters it will supply, but remaining supplied by the shunt capacitor banks and synchronous condensers and AC power supply. So in addition to this filters, we need to use other type of compensating equipment like a shunt capacitors as well as the synchronous condensers. So these are the two main purpose we'll use as a AC harmonic filters. And DC harmonic filters are only to reduce the harmonics on the DC line. So this is the difference between AC harmonic filters and then DC harmonic filters. AC harmonic filter will do the two purposes. One is reduce the voltage and current harmonics, as well as another one is the some part of the reactive power is going to be compensated in the AC side up to the allowable level. So now, but whereas rest compensation, as I mentioned, like capacitor, shunt capacitor and synchronous condensers, all these things will compensate that. Another, in the DC filters, only use it to reduce the harmonics. So not for, compensation and all. For that, it won't be required any compensation. And these are the purpose in the AC as well as DC. And types. What are the types of filters? So the filters at a converter station may be classified by their location and their manner of connection to the main circuit, their sharpness of tuning, and the number and frequencies of their resonances. So all these factors will influence of the type of the filter, whether we need to go for a single tune filter, a double tune filter, a high pass filter, or all these related to our requirement of our the application. Once I mention here, based on their location and where you have to connect in the AC side or a DC side, or I can say that before what you call it as reactor, or after the conversion and before the conversion, because many places are shunt compensators also you can use. So that is one of the factors. There is a location and the where they connected, that is another point. And sharpness of the tuning, so fine tuning, whether you have to suppress the fifth order harmonic or seventh order harmonic, like that depends on your frequency there you are going to be eliminated. All these things will decide the type of the filter. Another one is a location. Filters are located on both AC as well as the DC sides of the converter. And as I mentioned, AC filters are there and DC filters also there. So DC filters will not compensate anything, but it will reduce their harmonics. And more point is, DC filter side I can use reactor also. That is also the form of filter only. It's not, but whatever the functions of the smoothing reactor, that is replicated to that of the filter. And AC side we have other type of filter, single tune, double tune, all these things. Filters in the AC side may be connected either on the primary side of the converter transformer. So transformer concept is here, the supply is there, you are using as a tap changing transformers, and the secondary of the transformer only is connected to the valves. So that is only the normal connection diagram. That is the reason AC side may be connected in either of the primary side of the converter transformer. So preferably we will see that filters are located on the AC side as well as the DC side for the DC filters, or in the primary winding and secondary winding are there now, depends. So you can connect either in the primary side or in the converter side. Converter side is nothing but a secondary side, because primary winding is connected to the source and secondary winding is connected to the valve. So either of that is fine, but there is a territory winding is there some of the transformer. As you are aware that in the machines also territory winding is used in the substation transformers and all. Now because in the substation transformers primary winding is there, secondary winding is there. In addition to that, there is a territory winding, or also called as third winding. That rating of the territory winding is less than the primary and secondary. this territory winding you're connecting to the auxiliary components purpose, or suppose substation is there. We are giving input to the station and we are taking secondary is transmitting to the lines. But what about the large transformers are there in the substations and all? In that large transformer, we required some cooling mechanism, or you can say that some air blast or air cooled or oil cooled, like that many, and some office purpose also you may be required power. What is that, substation office or something. So for our pumping, some all mechanisms, whatever auxiliary equipment is there, for that we require as a power. And who will supply that power? You cannot tap from 11 kV substation or 33 kV substation directly. It is not possible. So then what they will do is, in a transformer they will use as a territory winding. That voltage levels are very less when compared to the primary and secondary windings. That winding voltage will make use of the auxiliary component. So that is the, call it as a, you can say that as a territory winding. In the territory winding is, if one is provided for that purpose, you can use. Filters are never connected to the secondary wall side winding. So only either territory winding side or in the primary winding side we can use. Since the territory winding is provided have a lower voltage than the primary winding. So this already mentioned, it is, we cannot use up to that much voltage level. This purpose is entirely different. That's why this winding is only lower voltages than the primary winding. The filters are insulated for the low power frequency and surge voltages, and therefore the cost will be less. The territory winding, however, add to the cost of the transformer. These windings are usually have a high leakage reactances, and which inherently forms a common branch in series with all the shunt filters, and complicated the computation of a possible resonance between the filters and the AC network. So another type of connection, you can see that series or a shunt harmonics may be obstructed in a passing from the converter to the power network or a line by high series impedance, and diverted by a low shunt impedance, or both. So we will see that first two kinds, which is in duality nature. Series filter must carry the full current of the main circuit and must be insulated throughout for full voltage to the ground. So because if you connect the series filter line, the whatever the current, the transmission current, line current is there, that has to carry by the series filter. So that is the reason that filter current capability must be there in the throughout, insulation throughout for the full voltage to the ground. So these are the series filters, and then shunt filters. You can observe that in the line it has to carry line current, but whereas in the shunt filter not that much current is required. Shunt filter can be grounded at one end and carry only the harmonic current, for which it is turned plus the fundamental current must smaller than that of the main current. So, but whereas series filter, it has to carry the total current, but whereas shunt filter, obviously it is connected to the ground. That is the reason only harmonic current of which it has to be carried, and hence shunt filters is much cheaper than the series filter, equal effectiveness. But I can see that only the connection itself it will differ. No, that is the reason if I both will filter out, but the thing is, if series filters are used, it has to connect in series with the line, therefore it has to carry the more current capability in the component in a filter. So for that reason the cost of that is going to be high. But Whereas in the case of shunt filter, it has to carry only the harmonic current. So, and AC shunt filters have another advantage over series filter in that the fundamental frequency in the former supplies the needed reactive power, but the later consume it. So, normally the series filter cost will be high because it has to carry more current, and for these two reasons shunt filters are used in the AC side, and on the DC side the DC that is what AC side preferably will use as a shunt filter, and DC side there is a DC reactor which is obviously as a series element constituting of all are part of the DC filter. So DC reactor you noticed in the previous classes also, where you are connecting there is a controller. After that controller output terminals is connected to the DC reactor, and then only you are passing through the line. So we have to filter out that DC harmonic. It must withstand high direct voltage to the ground and high direct current. It serves several additional functions, however, that requires series connection. The remainder of DC filter consists of shunt branches, and the filter could be as a delta connected, but connection offered no advantage. Therefore, star connection with ground neutral also will be used. Then sharpness of tuning. So I already mentioned now in the previous connection wise location and the type of connection and type of tuning. So all these just briefly I explain one and two sentences. Sharpness of tuning. Two kinds are used. One is the tuned filter, which is sharply tuned to one or two of the lower harmonic frequencies, such as fifth and seventh. The tuning filter is more important than any other. You can able to select the specific filter or specific harmonic. To filter out that harmonic we can use as a tuned filter. So that's what I mentioned here. There is a tuned filter, then you can tune one or two. Suppose if I use only single tuned filter, directly you can filter out that particular harmonic. Let it be fifth harmonic if I consider. You design as a single tune filter to suppress as a fifth order harmonic. Whereas fifth and seventh I want to eliminate. Then what? Either of two options. Either you can use two single tuned filter to filter out fifth and seventh is one aspect. Other aspect is you can use as a double tuned filter to filter out the two harmonic. One is fifth and seventh, such a way that you can design as a double tuned filter. The damped filter, which if shunt connected, offers a low impedance over a broad band of frequencies embracing, for example, 17th and higher order harmonics. You can see that second kind is also called as high pass filters. I will show that the small diagrams for that. There is a characteristics of two types. One is they can analyze under design of tuned filter and design of high pass damped filter. We can use that. So this is the single tuned filter. Anyhow, we'll get a complete design part after this. Single tune shunt filter and impedance versus frequency, because this level you can see that is going to be suppress your harmonic. That is another one is a second order damped shunt filter. Then automatical impedance it is going to be change impedance versus frequency, and this is the just example. Now we'll see the types of AC filters. So you have different types. One is the what you call it as band pass or tuned filters. Both are same. Band pass filters or tuned filters. Tuned filters are dividing single tuned filter and double tuned filter. There is a, just I mentioned, single tuned filter is used to filter out the specific order of the harmonic, that we can use as a single tuned filter, and double tuned filter is used to suppress the two specific frequencies of order. Another one is high pass filter, that we have as a second order filter and C type filter. So these are the some of the types of filters are there. And another one is the configuration of these filters and their impedance characteristics, function of their frequency. I will show that black diagram or something, I mean connection diagram for the each type of filters. So for that I will show the table. And single tuned filters are designed to filter out the characteristics harmonic of a single frequency. As I mentioned in the previously, this tuned filter is dividing as a single tune and double tune. And a single tune is used to filter out single frequency harmonic, and double tune filter are used to filter out two discrete frequencies instead of two single tune filters. Either you can use two single tune filters, or directly you can use as a double tune filter. Advantages are only one inductor is subjected to line the impulse voltage, and power loss at the fundamental frequency is going to be reduced. And second order high pass filters are designed to filter out the higher harmonic. So there is a second order high pass filters are designed to filter out higher order harmonics. So the tuning of these filters is not a critical. So because higher order harmonic itself is a low magnitude, so tuning is not much difficult. The losses at the fundamental frequency can be reduced by using as a C-type filter, where the capacitor C2 in series with L provide a low impedance path to the fundamental component of a circuit. So this is the connection how we are using as a C-type filter and all. I will show that anyhow diagram after this slide. A typical converter system, a 12 pulse converter, has double tune or two single tune, both are depends on your requirement. Either you can use as a two single tune filters to suppress to a double harmonic, or directly you can use that. To filter out 11th and 13th order harmonic, you can directly use as a double tune filter, and high pass filter to filter out the rest of the harmonic. So here the major, suppose if you use as a 12 pulse converter, as you are aware that in a AC side, like you can see the formula for 12 pulse converter, the DC harmonic is H is equal to NP, and this one will be H is equal to NP plus or minus 1. This is the order of the harmonic. So now let it be P is a 12 pulse and N is 1, 2, 3 and so on, or N or P, any notation you can follow. Then here is a 12 minus 1, that will give as 11, and another one you can see the 12 plus 1, 13. So these are the 11th order harmonic, and then 13th order harmonic is going to eliminate by make use of a tune filter. So I need as a these two, 11th and 13th. So what we have to do is we can make use of a double tuned filter to suppress 11th as well as the 13th, or you can use two single tuned filters, you can suppress as a 11th and 13th order harmonic. And the rest of the order, you can see that suppose here is N is 1, we got it 11th and 13th. If N is 2, then what we can, 24 minus 1 and 24 plus 1. So that will become as a 23 and 25. So in that aspect, we can notice one thing, for other than that order of the harmonic, we can able to use as a there is a higher high pass filter. So for the low pass, you can say the tuned filter is used to 11 and 13th harmonic, and other than that harmonic we can use as a high pass filter. So these are the different aspects how to use these filters. All the filter branches appear capacitive at a fundamental frequency and supply reactive power. And these are the some types of AC filters. Or you can see that single tuned filter. You can simply C, L, and R. You can connect it in series. That value of design RLC such a way that it is going to be eliminated the specific order of the harmonic, and this is the impedance versus frequency diagram, and that is for single tune. And another one is a double tune. So what is the double tune is here? Two single tune filters you can use it, or directly you can use this connection diagram. It will become as a double tune filter. So now this is one order of the harmonic and this is the another order of the harmonic, because this is the frequency line, no? So you'll get suppress the two frequencies. And the second order high pass filter and high pass C type filter, you can use this type of filters to suppress the higher order harmonics. So I will just explain one sentence for this what is single tune and all. Later we will design how to design relations, impedance relation, and then we'll consider what is the minimum cost of the filter. All these we'll see that. And single tune filters are designed to filter out the characteristic harmonic of a single frequency. And similarly, double tune filters are used to filter out two discrete frequencies instead of two single tune filters. And main advantage is just the previous slide I explained. And high pass filters of second order are designated to filter out the higher order harmonic, and tuning of this is not a critical. And C type filters can be used to minimize losses at a fundamental frequency, as they lack containing C2 in series with L offered low impedance frequency. Advantages of high pass filter: no sharp tuning is required. The high pass filter is used to filter out the higher order harmonic. So the advantage is no sharp tuning is required, and it tolerates relatively large steady state frequency variation. Third one, it reduces the transient voltage due to large resistance. However, it has higher losses. AC filters are designed to reduce the telephonic interference. So this is also one of the major problem. Injection of the harmonic itself I mentioned, there is a 4 or 5 issues I mentioned there, and at that point one of the main problem is this will interference with the telephone lines. The telephonic interference is going to be reduced. There is a sum of the factors we need to consider also. Anyhow, that will come next. This can be measured by one of the following parameter indices. So how this telephone interference AC filters are designed to reduce the telephone interference. For that, you are using as a sum of the parameters, that you can see that harmonic distortion factor. What is that harmonic distortion factor? You can see that D is equal to summation H is equal to 2 to M IH ZH by V1 into 100. That is the formula. Based on that value, we can see that harmonic distortion as well. The harmonic current IH means ZH is harmonic impedance, and V1 is the fundamental component of line to neutral. M is the highest harmonic consideration. So all these factors, just you substitute the data is here, you can able to find what is the harmonic distortion. That is one factor. Another factor is telephone influence factor. These are all empirical relation. There is no proof for this. They used different conventional, and they changed some of the parameter, and finally they decided these are the factors. One is previous one is a harmonic distortion, another one is a telephony influence factor, and third one is a harmonic form factor. So that is a telephone harmonic form factor. So all these values will decide what is your what you call it as AC filters will reduce the telephone interference. So we can make use of that, and we can get it as a relation how this is going to be minimized. Now we'll go for design single tuned filter. In practice, a filter is not always tuned exactly to the frequency of the harmonic that is intended to suppress. So now I think I already quoted in this sentence in the previously. There is a third order I want to suppress. Let's consider 150 Hz frequency we are designing as a filter, either in the bidirectional way, whether thing may happen in the source side or maybe in the filter side. Let in the source side we consider what is the intention there. I want to suppress 150 Hz frequency, need to eliminate. But the source I consider a 50 Hz, that's why I got it 150. But source may not be 50 Hz, that may be fluctuate. So that is the reason it may not be exact. Or on the load side, or I can say that filter side, we are using as an inductor, capacitor and all. No, some value we used and we design it. Later what will happen due to current pass through that, or due to the effect, or due to aging factor, all these things, that value of the inductance and capacitance, whatever we used initially, that may not be carried forward further in the long time. So there is a chance of getting the variation in the filter side also. That is the reason. I will show that reasons also. So this is not always exactly to that of the particular frequency. And one thing is, as I mentioned, power system frequency and harmonic frequency may be changed. So harmonic frequency we consider 50 into 3 for the third order. I call it as a 150, no? But what will happen? The 50 may not be there, that 49 let's consider, or 48. So 48 into 3. So that is also one of the reason. Power system frequency, and hence the harmonic frequency may change. And another one can see that inductance of inductor may change. So like that is all about the source side harmonic frequency. But once the filter side if we come, we use the so and so inductor value of that inductor, whatever you placed in a RLC is there, no, in the series combination, the single tuned filter, that inductance may be changed. So in that case also it may not be. So another one is the capacitance of a capacitor may change, and change in the capacitance is more significant than change in the inductor. So either inductor value changes also, the design part side will change, either inductor or a capacitor, that also going to change, because of again there is a change in the temperature, because the temperature changes, this factors is going to be influenced, and these filters are designed to filter out the characteristic harmonic of single frequency. It will be suppressing lower order harmonic. So you can see either 5th, 7th, 11th, 13th, etc. and so on. It may be 6 pulse converter. If you go for 12 pulse converter, again this two is going to be suppressed, and this third may not be there because it starts with pulse number 6. 6 into 1, 6, and minus 1 it will give as a 5, and plus 1 it will give as a 7. So for the 6 pulse converter we have 5th order and 7th order. For the 12 pulse converter we have 11th and 13th order harmonic. So these are the harmonic. You can see that there is a either lower order harmonic is going to be suppress this design. And now you can see the single tuned filter CS, LS, RS is the filter component. For that impedance versus frequency is this one. Now I want to design this filter with some relations. That's so it consists of a capacitor, reactor, and series with the resistor, and is tuned as a specific harmonic frequency. So now you consider some specific frequency and you have to design RLC or CSLSRS. Now the filter impedance is given by use this formula. What is the filter impedance? Because all are in series, no? RS, let it be R, and then there is a L and C also connected in series, then omega L, then minus 1 by omega C. And at resonance frequency, the impedance is the lowest and is equal to pure resistance. So under resonance condition, impedance is very low, as you see that impedance versus frequency diagram. Under resonance condition, the impedance is a lowest and is equal to R. So in that case, ZF is equal to R. Now this is our resonance condition. So omega is equal to omega n, that is equal to 1 by root LC, is a tuned angular frequency in radians per second. If filter is tuned to angular frequency of omega n, that means omega n is equal to 1 by root LC. This is the one relation we have, that omega n is 1 by root. So then under resonance condition, you can see that X naught is equal to omega n L. That means that reactance of inductance is equal to the reactance of capacitance. So that will give as a X naught is equal to root of L by C, and quality factor from that I can write X naught is equal to R cube. And now deviation of the resonance frequency for frequency omega other than the tuned frequency. Now there is a deviation, I told, no, whatever you design, but the frequency may change some deviation, that I call it as a delta, and delta omega n, just to cross multiply these two, delta into omega n, you'll get it as a omega minus omega n. What is the difference? Is the resonance frequency for frequency omega other than the tuned frequency. So this is the other than the tuned frequency, there is a change we can consider for our source side or maybe in the filter side. Tuned frequency omega n, I can represent X naught is equal to RQ, and C is equal to this one, we got it from this expression. We can see that C is equal to 1 by omega n into X naught, because what they mention, X naught is equal to 1 by omega n into C. So from this simply you can write C is equal to 1 by omega n into X naught. So what is X naught? So X naught is equal to RQ. You just substitute that instead of X naught, you can replace into RQ because R is connected in series, no, L and C, and R is, and Q is a quality factor. So now similarly you can get it as a L value also. Once if you know L and C, you can use our impedance formula. As you know that omega is equal to omega n into 1 plus delta, and ZF is, this is our expression already known in initially. R, L, C are connected in series, therefore ZF is equal to R plus J into omega L minus 1 by omega C. Now you know what is L and what is the C, and simply you can substitute here, you will get it as a ZF. So you can make use of that in internal substitution, L value as well as the C value, we will get it as a some relation ZF is equal to R into this, and this also you can further simplify some factor of K and all. You can change where K is equal to this one, just simplification. I given internal steps also. This will be there in the derivation in my textbook HVDC rigid publication, but now it is not publishing. That is a local author publication. I used this derivation in my textbook directly. So K is our variable factor, and you can use that impedance. You can convert it into admittance fashion. ZF is equal to, this is one relation, and YF is equal to 1 by ZF, and from that magnitude you will get it as this is the factor. So now, or else you can further simplify this with the different variations. We can able to give the current and order of the harmonic voltage. You can find here. You can change the specific order. You will get it as a V5 or V7 something, and based on that you will get the current and what is the shunt admittance and what is this harmonic YFH, and all these things we can substitute. You will get it as a voltage factor. And in this quantity K is nothing but something constant. I replace this by something K, this factor root of 1 by Q2 plus 4 del square I consider as a K, and K can be calculated for the different values of Q as a function of delta. Variation of K with deputing factor delta, we will see that expression. These are the variation at a minimum point. So whatever it is occur by changing as a K. So once you vary that K and with different Q factors, we can able to plot your graph. So this is about the single tuned filter, and some more minimum cost of the single tuned filter and all we can see in the next class. Just there is small step. We can see that tuned filter branch for a particular lower characteristics frequency, that you can say that x naught is equal to root of L by C, and filter is tuned to its resonant frequency. Fn is omega n by 2 pi, and the tuned filter is tuned to particular harmonic frequency. That harmonics of that frequency are passed to each and dimension of the AC network. So that is all about single tune small design part, and we will see that in the next class design of the minimum cost tuned filter. At what instant you can get it as a minimum cost and all these things. So one more class is there in this unit. Then we'll start in the 5th unit, that is multi-terminal DC link, that is HVDC link. So that is a very small unit. You can see that, and I will give the assignment questions by today in LMS server, and you can make use of that and submit within 2 days. On Wednesday I will correct it and I will give the marks. Already internal mid 1 marks also completed, and one slip test completed. So rest of the related to internal part will complete as soon as possible. So I will share that PPTs also in the LMS server. You just glance once. So that's all the today's class. You give me the attendance, just post in the chat box and you can leave.